Good evening, everyone. Today's plan is to continue on Boolean algebra that we started on. And as I described last time, and I guess the TAs have also started discussing some of these things in the discussion section, Boolean algebra is really the mathematical framework in algebra with operators and such, which is designed for us to provide formal way of expressing what happens in our binary digital system. So it's kind of the math behind it. And roughly speaking, you can say that the gates and all that we've been talking about kind of correspond to the operators in this algebra. So in particular, and or and not, they are kind of like in our regular algebra, you have add, multiply, and additive inverse and multiplicative inverse. Those kind of things are the counterparts out here as well. Okay, so let's see how it works out. So just like any algebra, we have variables here, and those variables can take, in our case, two values, 0 and 1, because we are dealing with two valued things. Now, just remember, we use 0 and 1 just as a convenience. Any two things will do, A, B, true, false, whatever. Normally, we use 0 and 1, and also normally we call 0 to be false and 1 to be true. But yes, frankly, it's just there are two things. That's all that matters. We name Boolean variables much like we do in algebra, right? I mean, or in a programming language. And then also we allow for variables which are like vectors, if you may, or arrays, one-dimensional arrays. So they have indices, and so those indices could be like x1, x2, or whatever you prefer, right? So in programming languages, some programming languages allow you to say this is an array or vector of width n, and they go from 1 to n. In others, they go from 0 to n minus 1. In yet others, they allow you anything like start from n1 and go to n2. Okay, so depends. Same thing out here. There are different hardware, different frameworks for Boolean algebra might allow you different things. Okay, so that's Boolean variables. Then we have Boolean literals. Literally means that a variable or its complement. So we use the term literal to refer to if a variable x, then x and not x, which is the part out here. They're both treated as they're both called literals. Okay, so when we say literal, that's what it means. Okay, and then comes the notion of what's a Boolean space. So just like you have, so again, going back to algebra, right? I mean, we think of the space of real numbers, the space of integers and things like that. So likewise, we think of it in terms of space of Boolean variables. Okay, so so each Boolean variable. So if I have a set of n Boolean variables, then you can think of each Boolean variable as kind of representing a dimension of an n-dimensional space. So it's a little bit like, I mean, regular algebra, we think of like x and y. X represents one axis, y represents another axis. If we have x, y, z, we refer to as a three-dimensional space. So in our particular case, if I have n dimensions, then and each dimension is Boolean, right? So essentially, it would be something like this. Let's say three-dimensional. So 0, 1, again 0, 1, and 0 here, 1, right? So that would be a three-dimensional Boolean space. So in general, we have an n-dimensional Boolean space. Let's see, I see some. Yeah. So just comment, folks, please. If you have logistic questions, wait until the end, because I won't answer them during lecture, and by the time it's the end, they'll be lost in the chat. Okay, so please keep your logistic questions until the very end now. Okay, so back to this. If I have n variables, I can think of them as representing an n-dimensional space where each axis can take 0 to 1 value. And each point in this space, you can think of it as corresponds to a particular assignment of values that we are given to the different variables, right? So if I have 3 variables, then and let's say those variables are, let's say hypothetically x, y, and z, then x equal to 0, y equal to 0, z equal to 0 would correspond to this. So each point in this space is basically a particular assignment of values to those variables. So thus far, all straightforward. Continuing this thing, now, just like regular algebra, we have functions. So a function takes a bunch of variables as inputs and produces a Boolean output. So in our particular case, a function may take n inputs. So therefore, it is taking something from a space Bn and is producing a Boolean output. So it is producing a single bit, single Boolean variable. So for example, AND gate, 2 input AND gate, which so it is really going from B2 to B. If I have a 3 input gate, as shown out here, this as given out here, right? So you see that it is going from a set which consists of all possible assignments to those 3 variables. So in this particular case, there are 8 of them. That's what you see out here. Then this B3 in this case. Okay, so Boolean function, you can think of it as a little bit like a game, which where the input corresponds to the assignments to those variables. So you can think of them in our case, because there's 2 of them, so like a coin toss or something like that. And then output is 0 or 1, and we can say 1 means, let's say, true or false. 1 means true, 0 means false, or 1 means winning, 0 means losing. So you can think of it like a game where we are basically saying what input patterns correspond to the game winning, for example. Okay, so for example, one possible game would be the following. We'll say we'll flip the point 3 times. We'll call the first flip to be A, second flip to be B, the third flip to be C, and we will say the game is won if all 3 flips were won. So in that particular case, we would say output is 1 if all the 3. So if you're residing at 1, 1, 1, and in all other cases, it is a 0. So in particular case, I mean, it's sort of obvious that we're talking about the function here is a 3 input AND gate, right? Because its output is 1 only if all 3 are 1, right? Okay, so we can take this game view of things and again summarize it as a truth table, the like of which we saw before. So in this case, again, 3 inputs, so 3 columns corresponding to the input and output, and then only the final combination corresponds to output being 1, all the others are 0. So this is a 3 input AND gate. And actually, strictly speaking, in Logisim terms, in Logisim, you can also specify the width of the gates. So you can say 3 input AND gate with width equal to 1. So in other words, it's something like this. And I want to just expand upon it this point a little bit, because one of the students who came to my office hours kind of talked about it. So let's say I wanted to have express 2 gates, and I have 2 variables, A and B. Each one of them are 2 bits. So let's say A0 goes here, and A1 goes here, and B0 goes here, and B1 goes here. and output is C1, C0. So what I'm doing is I have two input variables, A and B. Each one of them are 2 bits. And I have an output variable C, that's also 2-bit. And bit number 0 of C is the ANDing of bit number 0 of A and B. And bit number 1 of C is the ANDing of bit number 1 of A and B. So I can write it this way, or in Logisim, for convenience sake, I can write it like this. Like you can think of, or whatever, diagrammatically, I can like write it like this, A, B, C, right? So it's really saying there are 2 AND gates, one operating on bit position 0, the other operating on bit position 1. In Logisim, when you have the AND gate, you can specify its width, bit width. So there is a difference between how many inputs a gate has and what the width of those inputs are, right? And of course, arbitrary bits don't make sense, right? I mean, I can't have, let's say, an AND gate where one input is 2-bit, has a bit width of 2, and the other has a bit width of 3. By definition, and they have to be the same. So one has to be just cautious on that front. But this is a compact way. What you're seeing out here is a compact way of writing the same operation being done simultaneously on different bit positions. In programming languages, this is like a bitwise operator. Any questions on this? Just this is digression, but just to get the syntax that Logisim and we use.
I'm sorry, Professor, can you explain again what that width means?
Like 2 wires, right? I mean, width meaning there are 2 bits. There is a bit called A0. So like A, there are 2 variables, A0 and A1, which are representing 2 bits of whatever we are doing. Recall in the previous lecture, we had talked about like temperature could be representing using 2 bits, or color was being represented using 3 bits, right? So oftentimes we represent information using a set of bits.
Gotcha. So 3 input AND gate with of 1 means like 3 inputs, and like each input is 1 bit.
Yeah. So this one is saying it's an AND gate with 3 inputs. Let's call them X, Y, Z, and output, let's say F. Each of everything is 1 bit. But if I were to, let's say, put like this, what's happening? Let's say I have this, then that means I really have 3 AND gates. Sorry, 3 AND gates. One operating on X0, Y0, Z0 and producing F0. Another operating on X1, Y1, and Z1 and producing F1, and so on and so forth. So these are 2 separate concepts, right? There is the variable, but the variable can have multiple bits. Very much like programming languages, right? I mean, let's say in Java or C, if I were to declare this, then X is the variable name, and it has an array length of 3. So there is X0, X1, X2, right? So think of like when we are talking about multiple bits, multi-bit variables, then it's kind of like an array. And we are doing an item-wise ANDing of entries in 3 arrays, X, Y, and Z. Sometimes people call it bit vector. So X, Y, Z are bit vectors of length 3, and I'm doing an AND operation on those vectors. Okay. Any questions on this? Let's see. Okay.
Would the truth table be different for multiple wires for a bit width of say 2?
Well, technically there will be 2 truth tables, one for position 0 and one for position 1, except that they will be the same. So in that case, you can compactly write them as saying, for example, let's say I was doing this, right? Sorry for going all over the map, but let's say I was saying I had 3 variables, X0, X1, X2, and this was, each one of them was a width 2 and produces the output 2 with F, right? Let's say I had that. So that's really saying F of 0 is x of 0 ended with x1 of 0 ended with x2 of 0, and likewise a similar equation with ones. So you could write it in that case saying x0 of I, x1 of I, x2 of I is f of I for all I in 0, 1, something like that, right? So you can write it more compactly. There's no like set rule for it. I mean, at this point, it doesn't really matter. And honestly, no one writes truth tables, okay, other than when we ask you in problem sets and all. Why do you think we don't generally, you will not be dealing with truth table in real life?
Maybe because they're a little slow for anything bigger than 2 inputs.
Well, not so much slow, right? I mean, that's huge. Imagine you're doing a combinational logic with, I don't know, 1,000 inputs. How many rows? 2 to the power 1,000, right? So we can't write those. So it's just the size there. The problem is with truth table is they're expressing everything, right? Like look at this example. 7 out of 8 rows are 0. One of them is 1. So it's very inefficient, right? In terms of the storage required. It's good as a manual aid, human aid, but not that great as a computational thing. Yeah, so okay, so I can, back to the one bit version, essentially I can say that the truth table here really corresponds to this function. So this is the function that we have. That's the Boolean function. Okay, so I can oftentimes kind of what the inputs are is kind of obvious. Oftentimes you can just write it like this. Okay, but strictly speaking, this is what is going on, much like you might write in like real algebra, kind of a conventional algebra. Let's say another example, 3 inputs, and we win the game if majority of the inputs are high, right? So in that case, if all 3 are high, output should be 1, and if any 2 are high, right? So this are the 3 cases. So that's why you see that there are 4 cases in which output is 1. So as we discussed last time, right? If in this particular case, there are 8 rows in the truth table, so there are 2 to the power 8 or 256 possible different functions of 3 inputs, right? So lots of 3 input functions, lots of possibilities out here. Some of them are interesting, like the 3 input AND gate or a 3 input majority out here. Many of them carry no particular significance, so we don't give them any names. Now, this particular one, we can write it as a corresponding expression, which is what is in terms of Boolean algebra, right? So the trick out here is we basically say that, look, output is 1 if we are in this row or this row or this row or this row. So we are really considering a function which has 4 cases, right? So those cases correspond to the OR, right? So case, this is case 1, right? So let's see, this little 0. So it corresponds to this guy. Case 2 corresponds to this guy. Case 3 corresponds to this one, so out here, and case 4 corresponds to the last row. Okay, so literally what you can do is you can take a look at each row and create a case for it, and those cases are going to be ordered up, and then each case basically says, so like if I look at this case, right, it's basically saying output is 1 if x0 is 0 and x1 is 1 and x2 is 1. So you can say x0 is 0, that means not of x0 is 1, so that's why negated. and then x1 and x2. So it's literally this term, right? Ending, a specific ending of 3 literals, right? Is basically saying, this is capturing what the meaning of this particular row is. Okay, and so likewise we have for each row. Let's examine like this row, for example. It's basically saying x0 is 1, x1 is 0, and x2 is 1. So it would be x0 and not x1 and x1. And that's what you are seeing out here on the second term, and so on and so forth. So I can take a function and look at those rows which are 1, and then create an AND term like this for each row, and then order them up, right? So this way, clearly the simplest function would be 1, which has no ones in it, right? In that case, f is 0. If only one row is 1, then that's like we are saying, just selecting that row, right? I mean, so there'll be just one AND term, there's no need for an OR. If, I guess the most complicated case would be if 7 rows are 1, because then you need 7 terms. Why is all rows being 1 not the most complicated case? Well, because if all rows are 1, then instead of writing ORing of 8 terms, you might as well just write 1, right? So it's a case of 7, which is the most complicated one, and there are 8 possible such functions, right? Because the 0 entry could be in any one of those 8 rows, right? So there are 8 possible 3 input functions, which where 7 rows would be high. Okay, so nothing deep other than just counting stuff out here. So now, as you can see, kind of there's like a parallel that we are already seeing, right? I mean, we can write Boolean expressions, we can write truth tables. Previously, we saw that truth tables correspond to gates and all, right? And here we saw that truth table corresponds to Boolean expressions. So clearly, there's some sort of a connection out here that's going on. So, in other words, we previously saw combinational logics could be expressed at truth table, right? I mean, if I give you a combinational system, you can literally say, okay, for each possible input, what's the output, and write it down as a truth table. Here we saw that Boolean functions can be represented as truth tables that we saw, or vice versa. Truth tables can be written as Boolean functions, and so what that means is that Boolean algebra could be used, therefore, to express combinational systems. And once we have an algebra, then we can do simplifications, and right, I mean, we can cancel terms and stuff like that. So we can play all those games, much like our regular algebra. So I can then optimize combinational systems. So that's why Boolean algebra approach is potentially interesting. Now, so what we are seeing is that a Boolean function can be represented many ways. We can represent it as a truth table, we can represent it as a logic expression, and there are other ways of expressing Boolean functions also. As long as you have some sort of a systematic structure, you can do it. So in fact, there's a whole bunch of others. There's something called implicant table, there's something called hypercube corners, there's something called decision diagrams and inverter graphs and all, right? I mean, there are tons and tons of formalisms, some of which are discussed in various other courses. But at some level, they are all equivalent. In the sense that they are all expressing functions. It's just some of them have some properties which make them convenient for some purpose, and therefore we kind of use those in that particular game. So each representation has strengths and weaknesses. There is one which is used quite a bit in digital design by the software tools which do the digital design. One little thing, I mean, in this course, you're going to be doing a lot of stuff by hand or whatever, like diving into it. In reality, in real life, nowadays, no one sits down and designs combinational logic. There are tools that do it for you. So what is far more important is, in a way, how do tools do it, not how humans should do it. I mean, if you were in 60s and 70s and 80s, maybe humans would be doing it, but not anymore. So in particular, this particular formalism, which is called reduced order binary decision diagram, or ROBDD, is used quite a bit by many of the tools. And the main thing is that it is what is called in math a canonical form. Does anyone know what canonical form means or canonical means? So what canonical, so this has nothing to do with this course. Canonical representation generally in whatever math and computer science and pretty much any discipline means that it's a unique representation. What it says is if I give you two functions, they may be written differently, but they're really the same function, right? I mean, in ordinary algebra, for example, a plus b plus 2b is really the same function as a plus 3b, right? So as long as they're underlying mathematically equivalent, in our case, they will have, for same input, they will have the same output, then representations which guarantee that whichever form you give, they're actually going to have the same representation. They are called canonical representation, right? So if I give you two functions with two expressions, they look different, but they're actually the same function. In a canonical form, they will look the same. And if that's the case, then testing two Boolean functions being equivalent is relatively easy. You just write them in a canonical form, and then you just check whether the two, the canonical form representation, whether they're identical or not. In programming language terms, it's like you can just do a bit by bit comparison of the data structure and say, hey, these are same. So it's pretty cool from that perspective, because oftentimes I need to check whether two functions are equal or not. For example, very trivially, I may be given a particular module which someone says, hey, it does this function, and they give me an expression. And I want to convince myself that that expression is same as the expression that I want. So then I could, that's a problem of equivalence checking. These ROBDDs can do that very efficiently because they're canonical. The flip side, though, is that in some cases, they may take an exponential amount of memory to store this thing. Okay, so they're not terribly efficient. By the way, this trivial way of writing expressions that I showed out here, right? This way, right? And then this is also very inefficient, right? If you think about it, in the worst case, I have to write 2 to the power n minus 1 such expressions, which is not very good. So not a truth table is obviously extremely inefficient. So they all have their kind of efficiencies and inefficiencies, and one has to kind of worry about it. Another one which is used quite a bit is thinking of it in terms of that n-dimensional space, or as a hypercube in effect, right? Because on each dimension we only have two values, 0 and 1. So let's say I have the combinational logic which is shown out here, right? What is it doing? It's doing x or y and with this thing, right? So it is doing x or y and it with z. Okay, so I can write it with this kind of a Boolean expression. Obviously, I can write it as a truth table with 8 rows, or I can write it, draw it, and then in a software, you can think of some sort of a data structure to represent it, where I could say I have 3 dimensions, the x, the y, the z, and then those corners where the function is 1, I'm going to put a blue dot, and those corners where the function is 0, I'll leave a gray dot. So in this case, as you can see, the output would be high if z is 1 and either x or y or both are high. So there are 3 possibilities, right? So z is 1 means I'm in the upper plane, right? And then the 3 corners correspond to x equal to 0, y equal to 1. This is this corner. Sorry, x equal to 0, y equal to 1. Both x and y being 1, and x equal to 1 and y equal to 0. So those are the three cases. Now you might say, okay, I mean, drawing is painful and all, but remember, inside the computer, I'm not drawing it. I have to store it in some sort of a data structure. And some of you I know have gone through programming courses, and also hopefully you can think of data structures that I can use to represent such cubes, right? Such n-dimensional cubes with the coordinates of their corners, right? I mean, I could, so one trivial way I could do it is, I can, well, okay, so let me ask, can someone think of, in whatever programming language of your choice, tell me a data structure where I can store the colored hypercube for a Boolean function. How might you do it? I don't know if anyone knows Python. How can you do it in Python, for example, or how will you do it? Or any language of your choice.
What do you mean? Oh, sorry.
No, all you, please.
I was gonna say maybe a matrix for each
Okay.
dimension. Like you put another dimension in the matrix for each dimension of the cube.
Okay, fair enough. So in some programming languages, you can have n-dimensional arrays, right? Matrix. So I can create a matrix like in C or Java. I can create something like this, right? I can say my cube with size 2, 2, 2 in 3 dimensions. And so now I have basically I have a matrix which has a total number of 8 things, right? I mean, so I could certainly do it that way. And Python also, there are matrix-oriented data structures. You can use a list, right? You can just say there is some particular order I will assign to all these cubes, just a list. I could do that. I can use a dictionary. There's no shortage of data structures to represent these things. It always will boil down to what operations you are going to do it. And in our particular case, the tools seek to do various kind of optimizations, right? I mean, so they optimize for it. And the other thing is you want it to be compact. So those kind of issues come into play. But as you can imagine different ways you might represent this thing in software, and that's what the tools do.
Out of curiosity, how is that hypercube in software different than representing just a truth table in software?
Because you are retaining some structure. So we will see later, it's the operations we are going to do. So truth table basically says represent the rows in a sequence, right? So there is no neighborhood relationships there. Whereas here, it is important to know that these two are next to each other somehow, right? So I should easily be able to go into one to a neighboring one, or talk about which ones are on the same face of the cube, for example, those kind of operations. Whereas truth table doesn't require that, doesn't need that, so that wouldn't have it.
That makes sense.
Okay. So we'll see shortly that that does play a role later, okay, when we talk about optimizing functions. Binary decision diagrams, they kind of another representation. They're like a graph-like representation, again, very popular in software tools which do this thing. And what they do is it's a diagram which is organized in a layer. And so you can say each layer corresponds to a different variable. So this is layer A, this is layer B, this is layer C. And then finally, I have the output layer. Okay, so this is output. And kind of the idea is that we start from a root node corresponding at the first layer, A. And it's kind of like I'm traversing a road. At every point, there are two choices with this variable A. So A equal to 0, A equal to 1. And so now I reach, if A equal to 0, now I reach the B layer along this path. If A is 1, I reached along this path. Then now I look at B, same issue. I examine is B equal to 0, B equal to 1. So again, I have two paths going down. And kind of the idea is that now in this process, we do some optimization. So for example, if we realize A equal to 0 and B equal to 0, then in this particular case, it doesn't matter what C is, output to 0. So we immediately go from B to this output equal to 0. So these two ones represent into two possibilities of output equal to 0, output equal to 1. So the idea in BDD is that we are trying to represent these different paths which can traverse through A, B, C, if not necessarily all of them, but in general through all three of them to reach one of the two outputs. So in this particular case, for example, if I tell you A equal to 1, B equal to 0, C equal to 1, so then you will say, I'm going to take this path, then I'm going to take this path, then I'm going to this path, and therefore output is 1. Okay, so there are in general there are 8 possible paths, but because functions have some structure, so you may not have the worst case thing. So BDDs, while in some cases can take exponential amount of space, but in general, some of the information is lost, is not needed. So like you might have thought that in the C layer, I would end up with 4 nodes, but that's not the case. As you can see in this case, there's a single node out here. So depending upon the function, it saves space. So it turns out these ROBDDs, they make it very easy to do two things which are often needed, right? One is equivalence. I can check whether two functions are equivalent, and satisfiability, which basically says I give you an expression and I ask you the question, does there exist some assignment of input values such that the output is 1? Okay, so think about it. I give you a Boolean expression, and all I'm asking is a simple question, which is, for this expression, is there an assignment for the inputs? Let's say if there were three inputs, A, B, C. So I'm asking, can you give me just one possible way of assigning A, B, and C so that output is 1? Now you might say, hey, I mean, that sounds very simple. Actually, it's a super hard problem. Okay, so this kind of a again, those of you are doing some CS theory type courses and all, these things fall into the categories of problems which are exponentially hard. Okay, so but still we rely on heuristics and things like that. But if you have the right kind of representation, solving some of these problems become easy. Think about equivalence. If I give you two Boolean expressions and I ask you the question, are they the same? So I'm really asking you the question, for every input, do the two expressions give answers which are the same as each other? So how might you do it, right? I mean, one way to show two things are equal is to find a way to transform the first one gradually into the second one. The other way is to have a canonical representation, right? A standard representation, and convert each one of them into the standard representation and then check whether the standard representation looks the same, right? So these ROBDDs, the special form of BDDs, take that approach. They're basically saying, let's convert the function into the standard form and then almost canonical form, and then by definition, if the two functions are the same, then they will have the same representation in the canonical form. So that's the attraction of this particular thing. Now, I didn't tell you what ROBDDs is. I've just shown you the BDDs. But sort of this is that's kind of the nice property of this thing. You think about it, like if I give you a truth table of two functions and I ask you, are those two functions the same? Then what's the complexity? Well, you have to compare all the rows. And if there are 2 to the power n rows, you'll have to do 2 to the power n comparisons. So it's exponentially hard, right? In that case. So ROBDDs have the property that depending upon the function, it could be very simple to check. For some functions, it could be exponentially hard. In worst case, it can be exponentially hard. But in case of truth table, you'll always have to compare an exponential number of rows. So while truth table is canonical, it's not very efficient storage-wise, and it's not very efficient to check for equivalence. Any questions on this?
For the diagram, Is there like any reason why the 1 is like a full line and the 0 is a dotted line, or is that
Oh,
just
is it just
like
just visually?
all right? Thank you.
Nothing special. Yeah, just visual. Okay, so that was BDDs. I mean, look, there are like when I was a grad student ages ago, BDDs were making their way into this field, and there were like entire courses dealing with this stuff. Okay, so it's a deep area of research, and then this problem of Boolean satisfiability was a super hot area for many years. There were competitions and all, people trying to develop efficient ways. I mean, remember, it's an intractable problem, and barring so-called P equal to NP in computer science, this is going to remain exponentially hard in the worst case. But because it's such an important problem for, if nothing else, for computing industry, so there's a lot of work on algorithms which in practice for most things that we encounter are efficient. And so this Boolean satisfiability problem, there's a lot of sort of effort towards creating good heuristic algorithms which will work, generally speaking. Okay, so intuitively, what we've seen thus far is that there are many ways we can represent things. One thing, hopefully, that you'll also see is that some functions seem to be more complex than other functions, right? I mean, clearly, function 0 is super simple, or function 1, right? I mean, it's all entries of the truth table are 0, all entries of the truth table are 1. Those are simple cases. The problem begins to come when there's kind of no clear pattern. And then your Boolean expression is not compact, and sort of so what happens? So there's clearly some intuitive sense of, you can say, some functions are harder to work with, some functions are easier to work with. So there are these notions of like complexity of a Boolean function, and there are many such notions, and these different notions or these different measures, they seek to capture different types of complexity, if you may, different aspect of the complexity. So for example, let's one way of thinking about it is like, let's look at this thing. Let's say I give you these two functions, this one and this one. So one way I can say is that, left function is simpler, right? I mean, clearly when I'm writing it, it just has fewer literals, just ABC, and fewer operators. Whereas the right one has a lot more, right? I mean, it has 1, 2, 3, 4, 5, 6 literals, and it's doing 4 AND operations and an OR operation, right? So it's doing more operations also. So clearly, we can say this is more complex in terms of what we are talking about, that the representation, right? But maybe there is some other representation where sort of the left function is simpler, okay? Again, depends on the representation. But in this particular case, like if you're literally looking at how complex expression is, that's a reasonable thing to say. So I could also look at how much silicon area would it take, right? So what I can do is I can say, let me ship it to some sort of a design tool, these two functions, and see what I get, how big my design is when implemented on chip. And again, things will depend on the technology and all. Maybe in some technology that might be easier versus harder or whatnot, right? Okay. There is also other notions of complexity. So another one which in computer science gets used is query complexity. And kind of the idea is that it's the following. I give you a box which implements the function, right? So in our case, let's say it has 3 input A, B, C, and output is F. And you want to know what this function will produce for a particular ABC that you have. And of course, one way is I feed it all of ABC and it tells me the output. But you could imagine that I could I can begin to like how many queries I have to make before I can be sure of the output, before I can discover the function. So how many input bits I have to query about before I get to figure out what the function would be, right? So for example, if I give you the function a and b and c, and if a is 0, then I don't need to really ask about everything else, right? So I kind of start feeding a is 0, and the box can say, hey, I already know the answer. You don't need to tell me b and c. Okay, so that's some intuitive notion of complexity. There is also something called sensitivity, which basically says something about that what's the likelihood, what's the probability that if I flip a bit, so let's say I had given some input and there was some output, what's the probability if I change one of the bit, output will change. So like, for example, let's say I have a AND gate, and if both inputs are 0, 2-input AND gate, if both inputs are 0, output is 0. What's the probability if I flip a bit, the output will flip? Anyone? Like if an AND gate, both inputs are 0, what's the probability output will flip if I flip a bit?
0.
0, right? Nothing. But on the other hand, some functions would be the other way around, right? I mean, if it's an OR gate, 2 inputs are 0. What's the probability output will flip? I flip a bit. It's 1 in that case, right? So you can see that there is given a particular input, the sensitivity, in the sense that the output will change, differs depending upon what the current inputs are and what. And now across all the possible inputs, you can imagine I can do some sort of an average over that. So in a way, it is kind of capturing the sense that how many bits are important versus not. Clearly, some functions are very insensitive, right? I mean, the constant function 0 or the constant function 1, they are not very sensitive. And you can also realize they're super simple, right? So intuitively, sort of begin to align with some notion of complexity. So there are different ways. The one which is probably of most interest to us at the end of the day is this: how much area, right? How many gates it would take. And there was a little Piazza thread where kind of I had made the point that in silicon technology nowadays, transistors are cheaper, wires are costlier, okay, for a variety of reasons. And therefore, oftentimes, really, it's not simply how many gates, but it's really how many gates and how many wires, right? The combination of the two is needed for the answer. So, so I can talk about, one can talk about variety of these measures. The sensitivity one that I kind of talked about. So again, look at the circuit where the inputs were 0, 1, 1, and the output was 1 as shown. And if I flip this input, then the output doesn't change. If on the other hand, if I flip the lower input, then the output changes, right? So so we can reason about this sensitivity in terms of how many bits things are sensitive to. I'm going to skip this one over for now, but it's just another definition. Okay, so we can compute these things and all, and like I said, there are different measures, and probably, like I said, the sensitivity one may be interesting in some cases. It turns out there are other things you can worry about a function, like how fast would it be to compute it. Like constant function is super fast, obviously. On the other hand, some other functions may require more gates and may take more time to compute. How much energy would it take? That's another possibility, right? So there are other functions you can also think about, like how susceptible to imperfections a gate is, like what happens if a transistor goes bad, how how would the circuit be affected? There are a variety of real life issues that one might imagine, but typically the one which mostly we care about, things that we care about in this course are going to be mostly how many gates and how fast it is. Now, how fast, by the way, one way of thinking about how fast is, what is the longest path I can take from an input to output, right? So typically for each gate, you would have some delay number, and then I could talk about, like, this circuit out here, I need to go like this. So it's a delay of an OR gate and a delay of an AND gate and ORed together. Whereas going from bottom one is quicker because I'm just going through an AND gate. So the speed of a function in a way intuitively corresponds to how deep the representation is going to be. And again, we'll see later that all functions can be represented with a depth of 2. So there is a little bit more to it, which is like a 2-input AND gate is going to be faster than a 3-input AND gate. So it also matters how many inputs your gates have. That play a role also. So variety of measures. Okay. So now what Boolean algebra lets us do is, given a function, we start with some representation and then we can play with it, apply rules of algebra, and then attempt to simplify it to achieve some goal that we have, minimize some notion of complexity that we kind of care about. Now, in order to do it, just like in normal algebra, we make use of properties that let us simplify, play with these expressions. So like in algebra, they start with some axioms. There are some things that we just assert to be true. And then we kind of start work from them. And the truthness of these axioms is kind of, at some level, we argue, is intuitively obvious. But frankly, I mean, in a strict sense, there is no proof. It's just it's a consistent framework. Okay, so what are axioms of Boolean algebra? So there are these 6 axioms. So remember, there are 2 values, 0 and 1, right? Or whatever, apple and orange. Okay, so I can we can start by saying, so there is 2 identity operations, which is basically saying that there is 0 and 1 ANDed together is a 0, and 1 ORed with anything is a 1. Okay, actually, and then idempotence is actually, I'm sorry, this probably should have said 0 and x. Okay, so 0 ANDed with anything gives a 0, and 1 ORed with anything gives a 1. So 0 is the multiplicative thing, and 1 is the additive, or 1 is working with the OR. 1 and x is x, and 0 or x is also x. Not 0 is 1, not 1 is 0, right? So we are basically defining these 6 possible things, and intuitively kind of they mimic each other. Okay. So now, starting with these and these alone, there is a set of properties that exist. So these properties are derivable. Okay, that's important, right? These are, you don't need, you should be able to prove them from the axioms, right? And so it's saying AND operator is commutative, order doesn't matter. OR operator is commutative, order doesn't matter. So much like plus and multiply in our regular algebra. Associativity, that is the way we group, doesn't matter within each operation. distributivity, and distributes over or, and or distributes over and. Okay. Now, this place, there is a different from our usual algebra. In our normal algebra, A times C plus D is AC plus AD, but A plus BD is not A plus B times A plus D, right? So in our regular algebra, distributivity holds only for in one of the cases, not the other case. Idempotence, which X and X is X, and X or X is X. Absorption, so X and X or Y is the same as X, and the corresponding thing in the right hand side. So intuitively, this is super useful because I can easily eliminate things, right? And it's basically saying that it kind of well, one way of proving these things is you can always construct a truth table of both sides and kind of show that it is true, right? So that's one way you can do it, but you can also algebraically kind of show the equivalence out here. Combining, this is another property, right? So it's basically kind of canceling out Y and not Y in these cases. And finally, probably the most important of these properties is the so-called De Morgan's property. So it basically says the inverse of X and Y is the OR of their inverses, and likewise inverse of X or Y is the AND of the inverses. And this is a special case of a more general duality property that sort of exists. So the nice thing out here is, if you look at these cases, they let us go between AND and OR. Okay, what the left hand side is saying is this is the same as and the right one is saying okay. So so essentially I can move inverters from output to inputs or vice versa, and then change AND to or to AND. And that's very powerful because I can kind of go back and forth. And now this suggests to you something else. This says that using a NAND gate, I can implement an OR gate. Anyone sees that at home? Like how, remember previously I shown that using a NAND gate, I can implement a NOT gate, and using the NAND and the NOT, I can therefore implement an AND. Now, what I'm suggesting here is that this De Morgan's tells me how I can implement an OR gate using a NAND gate, using NAND gates. Does anyone see how?
I mean, if you just do the NOT of the quantity of not X and not Y, you just get an OR gate.
Yeah, so I can indeed. So I mean, okay, one there are variety of ways you can kind of think about it, right? I mean, so I have an NOR gate. Well, okay, start with the left hand side, right? So we see that the NAND gate is equivalent to this thing on the right hand side, and so if I put an additional NOT gate here, then I have an OR gate. So that means if I put inverter here, then I get an OR gate. And we already know how to do inverter using NAND gates. So therefore, using NAND gates, I can do an OR gate. And so from a NAND, I can go to NOT. From a NAND, I can go to an AND. From a NAND, I can go to an OR. And from a NAND, therefore, I can also go to a NOR, right? So all of those things are covered just using our NAND gate. So which is kind of, again, NAND is universal. And likewise, NOR is universal. Okay, so these are all the properties, and we'll ask you some questions around these. I mean, you can, like I said, brute force way of verifying these is just write down the truth table for the left side and the right side of each equality and verify they are the same. Or you can algebraically, it's always fun to kind of algebraically try to go from one to the other also. Okay, sometimes force you to do it. Yeah, this is just a truth table. So I'm not going to I'm going to skip these. These are just verifying by drawing the truth table. So you can, I'll leave it for you to just flip through these things. Okay, so the textual form of De Morgan's theorem says the complement of the product of variables, product meaning and, is equal to the sum, namely OR, of the complement of the variables. Okay, and likewise the other De Morgan variant. Can you prove this thing algebraically using other things? It's always a good fun exercise to kind of do that. So this goes to kind of strategies for proving equivalence, right? I mean, if I say, here are two functions, are they the same, right? Now, one way for you to do is to do a truth table for each one of them and then make sure the truth table is identical, right? Each row corresponds. But for large number of variables, that can be pretty painful to enumerate. Oftentimes in real designs, you may have combinational logic which have a few thousand inputs. Okay, so you're dealing with 2 to the power of a few thousand. So can be pretty tedious to say the least. So this is where other strategies come into play. So one thing you can do is you can say, I'll apply Boolean properties. So that systematically I can transform function f to function g, right? So I have to find a way to transform these things to get to from f to g. So I could do that. A strategy 2, which generally I find often easier. Well, actually, no, not strategy 2. Strategy 2 is go in the reverse direction, g to f. So same thing. Strategy 3 is the following. So here I kind of make use of the fact that if two things are equal, then for all inputs, either they are both 1 for a particular input or they are both 0, which we also call as XNOR, right? So we can basically say that the following must be true. Either f of a and g of a, either that is true, right? F and g are both giving output of 1, or not of f and not of g are both true, right? So either both f and g are 1 or both f and g are 0. And or means, right? This one is says one of these two cases is true for each value of ABC. And that means we are trying to prove that this expression is always 1. That is, by applying Boolean expressions, I can reduce it systematically to a 1. And that's usually, it can take a longer time, but I generally find it to be a foolproof strategy. Whereas going from F to G or G to F always kind of requires like figuring out what property to apply and all, whereas this one always will work. It just may take longer. It's a little, the analogy here is a little bit like, if you're trying to solve a maze problem, the brute force to pay where just follow the left wall and eventually you will reach the destination. But of course, you could hunt for something smarter and clever, which might be shorter, but follow the left wall will always work. It's the same thing out here. This strategy will always work, but we are dealing with more complicated expressions and all, but it works. So hopefully all of you see it why it works. Let's imagine f and g were not equal. That means that there would be some value of ABC where f would be 0 and g will be 1, or vice versa. F would be 1, g would be 0. And in that case, both parts, right? Both the left part of OR and the right part of OR would be 0, and the output would be 0 in that case. Any questions on this one?
Yeah. Is there any way to do this? Like if you were to do it on the computer, does it have to plug in every possible value and make sure that that equals 1?
Okay, so firstly, of course, the trivial answer is there are tools out there which do equivalence checking, okay, symbolic equivalence checking. So I guess if now, so the real question out here is how do they do it? Okay, and right, I mean, so it's an equivalent of asking the like if you have access to Mathematica or something like that, they do in ordinary algebra, they check for equivalence of function and all, and they have strategies built in. So tools which do this kind of stuff, they usually apply these kind of techniques, okay? Or and they try to find a good search strategy. So it's really fundamentally a search problem, okay? You essentially have a source and a destination and a complex web of ways of going, and you're trying to find, is there a path? So that's what the tools do. There are so-called theorem prover tools, which people who work in programming languages and all kind of use quite a bit. I think there's one from Microsoft called Lean, for example, which does these kind of things. I think Wolfram Alpha also provides these kind of capabilities. But more importantly, there are tools which are specifically used by chip designers and all, which have these functions built in. So like there's a tool called Synopsys is a tool. Okay, so there's a company called Synopsys makes these kind of tools, other such companies. So those tools are called logic synthesis tools. Okay, and they basically provide you these kind of capabilities built in. Okay, if you were to write your own program, then in Python there is a package called PyEDA. It provides functions to do it. There are some other packages also in Python. So yeah, so look, these kind of things are so widely necessary that there's a lot of stuff out there.
And
would you be proving equivalence to check like a transformation, or what use would there be in that?
What use of thing is, so one most common use is the following. Your customer gave you a specification in the form of a logic function. You went ahead, implemented it. Your output is now a chip. How do you know that along the way no bug got introduced? So what we do is we take that final silicon and then we map it into a gate network. And then that gate network can easily be expressed into a logic equation. And now we have to show that the two are the same. So it's to verify correct implementation. Okay. So that's probably the most important use for this thing, verification. Yeah. So, and like I said, the issue is that along the way, maybe some tool was buggy, or along the way, something happened in the process of like a wire is not connected properly or something like that. So those kind of things. Okay, so yeah, and there is a dual of this, which basically proved this. Okay. By the way, these two things, this is the same thing as saying and this thing is the same as saying right. So the top one is saying either both are 1 or both are 0. The bottom one is saying it is not the case that the two are different. Okay, so here is kind of an example of how we can do the kind of manipulations we are after. I'll let you kind of work it out at home to see what the details are. It's basically tedious algebraic manipulation, but kind of the idea is, let's say we are starting with this expression, right? And I can apply idempotence and commutativity. So again, I'm taking this guy and based on applying these things, I end up with kind of I expand the operation. So usually the strategy when going from one function to another generally boils down to you expand and then contract. So kind of you expand into something more general and then you contract along a different path to get to the other function that you have. So we expand this way, we apply absorption. I'm not going to walk you through these things. So we go through a series of properties, and after some systematic things, we kind of so we sort of manipulate it these ways, and we end up with the simpler function in this particular case. Okay, so what looked kind of more foreboding at the beginning is actually a much simpler function. F A B C is A and C, or B and C, and or A and B. Okay, I guess more pertinent to us, what does this function do? Like, what in more plain English, what would you say this function is doing? So look at this guy. What is it? What is it?
It looks for a pair of ones at least, or pair of trues.
Yeah, so it's basically saying at least so actually, while it is not explicitly stated out here, it's actually doing the majority function, that majority of inputs are 1. So it's saying A and C, A or both A and C are 1, or both B and C are 1, or both A and B are 1. And you can imagine, you can sort of think over this and say, if A, B, and C are all 1s, then 2 of these cases will be 1. Oh, sorry, all 3 cases will be 1. So that's what it's doing. But the idea, but the point is that when we started out, the initial expression, it wasn't really obvious what the function was doing, right? But the sequence of transformation that we did ended up with this simple function. So if someone were to, let's say you had some circuit and you just mapped it out, it was doing what is shown out here. But I claimed that this was a majority function. Well, you will prove it by showing that this function is equivalent to this function. And one way to do it is by this kind of a simplification, coming up with the steps. I always, at least intuitively, find it kind of hard to do this thing. Like you have to have some good intuition about the function. So generally speaking, I find the other strategy to be easier, but it can be more tedious, more writing. So, okay, so like in normal algebra, where you can kind of manipulate algebraic expressions, it's the same story out here, except the set of properties we have are kind of different. Okay, so this kind of leads to something that I had already said, that along the way thus far, that we can see that gates are able to represent each other. So I'm going to go this one quickly. If not was unavailable, we saw that we can make NOT gate from other gates. So we can make a NOT gate from a NAND gate. We can make a NOT gate from a NOR gate. We can make a NOT gate We cannot make a NOT gate from AND. We cannot make it from NOR. Sorry, from OR. Can you make a NOT gate from XOR? So if I give you an XOR and you convert it into something which inverts an input. So XOR truth table
There was an answer in the chat.
Oh, okay. Yeah, one an input. Terrific. Thanks. So you tie one of the inputs to one, the other will be inverted. If you have an XNOR, then you tie one of them to a 0. Okay, great. So we saw that. I think most of these things we have seen. So De Morgan also, I thought, right? We have seen this. I'm going to flip through this. Can I make an OR gate of a NAND gate? We saw that. So I'm going to skip through that also. So OR gate, we can do it NAND gate. So essentially, we can do a lot of these things. That leads to the main thing, that there is a concept of universality, right? That is, I can give you a set of gates and say that set is universal. If using that set, I can implement anything, any gate. Now, one way of thinking about it is, if I give you some gates, if I show that I can implement NAND using those, then I have proven universality, right? Because I already know NAND is universal. So in some senses, given any set of gates claiming that they are universal, I only have to prove they can implement NAND, or maybe I have to prove they can implement NOR. AND is not sufficient. NOR is, sorry, and OR is not sufficient, but AND plus inverter is sufficient, because AND plus inverter, I can do a NAND and then I'm done. Think about, I'll let you think about, is XOR sufficient? Is XOR, is if I give you an infinite supply of XOR gates, can you implement everything? And I will leave that as something for you to ponder about, and yeah, to see. Anyone knows the answer to it? Is XOR, like, quick, ready intuition whether XOR is universal or not? Okay, think about it, Google, find out. So let's move on. So I guess I'm kind of giving you a sort of a little, is XOR universal? Okay. Think about it. It's a pretty interesting thing. So, okay. So now let's talk about dual, minterms, max terms, which are important concepts. Okay, so the dual of a Boolean function, if I give you an expression, right, then to create a dual, what we do is we replace every AND with OR, every OR with AND, any 0 with 1, and any 1 with 0. These are referring to the constant 0 and 1. By the way, one other thing I just wanted to mention out here is, sometimes when we talk about universality, you can say that like the person, those who said using XOR, can I implement a NOT? So, and your answer was, yeah, we can, we tie one of them 1. What's really going on there is you're using an XOR together with a constant gate 1, right? Because that's how you are feeding a 1 to it. So just bear that in mind, that the NOT, to make a NOT, you need an XOR and you need a 1. Okay, so going back out here, oftentimes you may have expressions and all which literally do use the constant 0 and constant 1. So the idea would be 0 gets replaced by 1, 1 replaced by 0. So for example, if I give you the expression FAB is A and B or B and C, then its dual, which is indicated by this indicates dual, is wherever there is an AND, it becomes an OR becomes an AND. And in this case, there are no 0 and 1, so that doesn't change. Okay, so that's the dual. Sometimes students make the mistake and say, oh, if I have a NOT, I'm going to remove it. No, you don't. Okay, you don't touch NOT at all. Okay, so you're only touching AND and OR, and you're touching zeros and ones. Okay, now this is just a definition. There's no magic about it. This is how we define dual of a Boolean function. Okay, so why is it called a dual? Because that's how we define it. So find the dual of the following function. What do you think it is? Anyone? Just write it out in the chat. Yeah, good. Yeah. So Jake got it right. Okay, so that's the dual. Okay, so now the reason dual matters is that there is a property of Boolean algebra called the duality property, which says dual of a function applied to the complement of the input, inverted versions of the input, equals to the complement of the function. So let's just digest it. It basically says, if I take a function and I take its dual, right? So in the example out here, we had FAB and the dual of AB. Then it's basically saying, if I take the dual, but then instead of using the inputs as they are, I complement the inputs. That is, I do f of d, not A, not B. Then it's saying it's the same thing as not of. Okay, that's what the thing is saying. So, so literally this, right? F of the dual F, where I replace wherever, like instead of if the input was 0, 0, 1, then I will make the input to be 1, 1, 0. Okay, so I'll flip the input bits, and the result that I will get would be the same result as applying giving to F 0, 0, 1, but then whatever is output, flipping that, right? So input flipped, fed into dual, give the same result as inputs given to the original function, but then flipped in the output. Or you could equivalently write it as right. So I could also say flip the input, feed them into the dual, flip the output is the same as the original function. Yeah. Now, De Morgan's law is a special case of this duality property. You can convince yourself, kind of going back, that that's all that De Morgan has done. So this is kind of more, this is a generalized form of De Morgan's law. Okay, it's applicable obviously to an arbitrary Boolean expression, right? That this property would hold true. Okay, so and from this variety of other interesting things could be therefore derived. Is a very useful property. So yeah, anyway, so any questions on this? Okay, so so what's the dual of this F, which is written out here? And what is the complement of F? So again, just write in the chat. Okay, so let's see. Okay, so that's a good dual. Okay, and anyone wants to write the complement? Good, I think. Okay, so but one thing to remember is dual is not equal to complement, right? But what we do have is out here that dual applied on the complement is equal to complement of the original. Okay, so just sometimes people confuse dual and complement. Okay, so just wanted to sort of get that out of the way. Okay, so let's moving on. So that's dual and how it leads to De Morgan's. So De Morgan is just a special case of that. Now there is another very important definition, and it's called minterm. So if I give you a set of variables, let's say the inputs to a particular box, a particular system. So let's say there are n 1-bit Boolean variables, which are your inputs. So there is a special thing that we call as minterms, and minterms is an expression that ANDs all the variables, with the only caveat being that the variable is either as is or is in the negated form. So let's say if I have 3 variables A, B, C, then A and B and C is a minterm. A and not B and C is also a minterm. A and C is not a minterm because it's missing B. Okay, so every variable has to be present, but it will be present in a negated form. So that's the definition of minterm. Again, why is it called a minterm? That's the way it is. Okay, so how many minterms of 3 variables are there? 8. Yeah, right, because all 3 have to be present, and they can be present in 0 or 1 form. Sorry, positive or negative form. Okay, so
could you use parentheses as well?
What's the question?
Could you add parentheses as well? Could you group the?
Yeah, you can. I mean, so you can, if you so want, you can write A and not B and C, and that's fine. That's still a minterm. Although, I mean, try not to put them because it's conventionally not put, but you certainly could. Okay. Generally, I mean, I guess you could say it's equivalent to the minterm. The convention is to write without parentheses. Okay. Okay. So there's a counterpart. Now we are in the world of duality. So every time we have one, there's another version of it. Maxterm. Maxterm is an expression that ORs every variable, either direct or negative form. So these are the maxterms, right? So intuitively, if you kind of go back, minterm saying A and B and C, saying A is 1 and B is 1 and C is 1. So it's pointing us to a particular row in the table, right? It's pointing to the row A and B and C. It's pointing to the last row of my truth table, the one where everything is 1. It's basically saying for that row, then typically, remember in my truth table, if I have entries corresponding to 1, so remember one way we were writing it was that we just looked at the rows which were 1 and then we were ORing them together. So we later on see that one way of creating a function is to look at the rows where we are 1, look at the minterms for those rows and kind of order them together. Maxterms play kind of a similar role, but they focus on when the output is 0, as we'll see. So A or B or C takes a value 0 only when A is 0 and B is 0 and C is 0. So you can say that A or this maxterm here this is really kind of pointing to row number 0 uniquely, right? Because this max term takes the value 0 only when we are in row number 0. All the other places, this max term will have a value 1. So again, you can think of it as a way of pointing to a particular row. In case of min term, being 1 is important, and max term being 0 is important. So now there is kind of a correspondence between these. And so you can say, so let's say I had 4 variables, A, B, C, D. Now, very important out here that for our purposes here, we'll have to also define the order in which we are thinking about the variables. Extremely important. So in this case, let's say we agree that we are always going to write things in the order D, C, B, A. That is, the first entry in the min term will always be either D or not D. The second term in the min term would always be C or not C, and so on and so forth, and ditto for the max term. So it's convention. We could have picked the other way around, but let's say the problem stated that consider this as the order, right? So DCBA. So I can write all the 16 rows here, and I can number them, right? I mean, so row number 0 through 15, and it so happens if you kind of look at these, they also kind of correspond to the normal base 2 interpretation of these bit patterns, right? Like 0011 is the base 2 number 3, for example. Okay, so the row number kind of corresponds to, you can say, corresponds to this. What's the min term for this thing? So the idea is DCBA, D is 0 and C is 0 and B is 0 and A is 0. So min term is going to be that min term which takes the value 1 when we are in row 0. And that would be this, right? Not D and not C and not B and not A. Or consider, let's say, this guy, row number 9. So I need to find that min term which will take the value 1 when I'm in row number 9. So anyone orally help me? What should I write there?
D, not C, not B, A.
Yeah, D and not C and not B and A. Okay. And let's pick another one, right? Let's say I'm in this guy, 1100. So D and C are 1. So it would be D and C and not B and not A. Okay, so hopefully not too hard. For max term, it's the same game, except for row number 0, I need that max term, which will give a 0. So D is 0, C is 0, B is 0, A is 0. So it would be D or C or B or A. But let's play it out. For row number 2, it would be D 0, C 0, B 0, and not A. So max term you have to flip, right? Max term you are obviously putting OR, but very crucially, the negated form appears where the bit is 1. Okay. So that's the corresponding max term, right? So again, we put that min term, which will give a 1 for the bit pattern for that row, and we put that max term, which will give a 0 for that bit pattern. And I'll sort of go through the whole table. You can kind of just check it out on your own. Okay. Now, very crucially, we give names to these min terms and max terms. So min term, which corresponds to row number I, we call it as m of I, little m of I. So little m indicates the min term. So for example, in this case, this particular shaded entry is the second min term, m of 2. And likewise, we have max term. Again, it's by the row number. So we basically max term corresponding to row number 6 is m of 6, except that is indicated by uppercase m, right? So lowercase is min term, uppercase is max term. Okay, so now what happens? So all of these, yeah. So I can give all of these names, and now we can exploit the dual property out here. Like if you apply it, so it basically says complement of a minterm is the corresponding max term. So for example, let's say I take max term M5, which would be D or not C or B or not A. Okay, and we can verify it out here. 5, it would be this guy, right? D or not C or B or not A. And then we do the dualization. So we take complement applied to complement of the dual applied to the complement, right? So what we take the dual and then flip the literals, and you will see we end up with this, right? So it's basically saying max term is the complement of the corresponding minterm, or essentially De Morgan's. Okay, so that's the dualization. Now, why is this useful? This builds up to a canonical way of writing Boolean functions, which will make it so now this will give us another strategy to check equivalence, because if I have a canonical way, then I can convert any Boolean expression to its canonical representation, and then I can check the equivalence. And those canonical ways are referred to as normal forms. And in particular, these normal forms come in two variety: disjunctive, conjunctive normal form. Normal forms of a Boolean function. Now here I would caution you that if you go onto websites and all, oftentimes they have somewhat different they call somewhat different things as normal form. So be careful. You are supposed to stick with the way we are defining it here. Okay, so normal form of a Boolean function is a unique representation of the Boolean function. Okay, canonical representation. The disjunctive normal form consists of minterms which are ORed together. So remember, in our truth table, some entries will be 1. So one way of describing a function is saying which rows it is 1 for. And the minterm tells me a minterm is a 1 for its corresponding row. So if I were to OR the minterms together, then I'm basically saying the function is 1 if one of these minterm is true. Remember, only one minterm can be true at any given point in time. So for example, FABC is saying, let's say if this is a function, each one of these is a minterm, right? It has all the 3 inputs, either directly or indirectly. This one is little m7. This one is little m100, so 4, and this one is little m5. So it's basically saying m7 ORed with m4 ORed with m5. And other than permutation of these minterms, which you can again say, hey, I'm just going to sort them in increasing order or something like that, they are the same. So you could also call it a disjunctive sum of product form. Disjunctive sum of, you can also call it as sum of product normal form. Sum of product refers to that here I am ORing together some AND terms, right? Product terms. But the very crucial form is that because it is normal, we require that the AND terms be actually min terms. Not like, for example, A and B is a AND term, but it is not a min term. So for example, if I had written this, then it is not okay, because A and B is missing C. But I could convert it into a normal form, because I can say A and B is the same as A and B and C, or A and B and not C. And then I plug in the final one, A and not B and C. Okay, I can always expand smaller terms into bigger terms. This guy, this part correspond to this guy. And I'll let you figure out what property I used out here. It's using one of those Boolean properties, which tells me that this can be done. So, anyway, this is what we call as DNF, or disjunctive normal form. A very common mistake I've seen in previous years is that because you may visit some other website and all, and it may call this guy to be a disjunctive normal form. No, it is not. So, and we'll not accept it, okay? So whenever we say disjunctive normal form, it has to be min terms which are odd together, okay? We can also call it as SOP normal form, okay? Sum of product normal form, okay? That's the same thing. But if we simply say sum of product form, then it doesn't need to be normal. So this guy is sum of product, but it is not normal. Any questions here? Okay, so if not, there is obviously a counterpart, conjunctive normal form. So conjunctive normal form is max terms which are ANDed together in a product of something. So you can say conjunctive normal form is the same thing as product of some normal form. So here is an example, right? In this case, ANDing is being done, and then each one of these is a max term. And because AND has a higher priority, so you have to be careful. You have to put parentheses out here. And which max term is this? A or B or C? M of 0. Good. Yeah. So you can write things obviously more compactly also. Okay. So oftentimes we may just say normal form, sometimes people, right? When they say just the normal form, they're referring to the disjunctive normal form because it's a more common one which gets used. Okay, so why use normal form? Okay, well, normal form is unique, and particularly if you sort the min term or the max term in order, then it's really, really unique. And so if that's the, and remember, each min term, it appears exactly once and they appear in particular order, so we can easily compare functions, right? So if I give you two functions, what you can do is you can expand them and all until you get the normal form, and then you compare, or whatever, let's say disjunctive normal form, and then you can compare the two. So for example, we had this truth table from a prior lecture. Yeah, so I see a comment out here. There are essentially a way of writing a truth table in Boolean logic. Yeah, I mean, basically it's a way of writing either the 1 rows or the 0 rows, right? So the disjunctive normal form is saying this is a set of rows where the value is 1, and by implication, therefore, the others are 0. Whereas the conjunctive normal form is saying this is the set of rows where the output is 0, and therefore, by implication, the remaining ones are 1. So which one you're focusing on is the only difference. Yeah, great point. So you can also imagine that if I have a function where lots of rows are 1, maybe you might be better writing it in CNF form because there are very few 0 rows. If on the other hand, you have a function which has lots of zeros and few ones, maybe the other way around. But then the pattern also matters. So there is no sort of clear answer, but But in the worst case, like if you are only writing, let's say, DNF, then the worst case, you may need 2 to the power n minus 1, that many minterms. Okay, so going back to the truth table. So the distinctive normal form, we are going to do that. So in this case, we are going to focus on rows where things are 1. So we have these rows. Okay, there are 6 rows where it is 1. So we kind of write them down, and we are basically saying the output is 1 if we are in one of these rows. So either we are in whatever, this row or 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 this row. So that's
why is row 5 0? Row 5, why is it 0?
Why is row 5 0? 1, 2, 3, 4, 5. Current temperature is more than, yeah, interesting. I think it was because we were, oh yeah, this was the one where current temperature 0, 1 could never occur or something like that. I don't know. Let's see. Yeah, I'll get back. I just copied it from a previous lecture, so this must be some special case there. Yeah, I think it was vaguely because remember we had a modified version where we had introduced a don't care. So I think I suspect it's that version of the table. Okay. In any event, that part is kind of not very relevant out here. Just think of it as a truth table. Okay. Yeah. So which has this structure, and therefore these 6 rows are 1. So I can write whatever. So maybe it's not your digital thermostat, whatever.
On 5, both of them represent 60 degrees. 1 for current temp is 60 degrees, and 0, 0 for present temp is also 60 degrees. So they're equal. So okay. It doesn't mean.
Okay. So maybe that's why. Okay, cool. Yeah. Anyway, I guess the more important point out here is that imagine this was a truth table with these 6 things, right? So the DNF would basically highlight which set of rows are 1. So intuitively, in plain English, we are really saying output is 1 if whatever row I is true, or row j is true, or row k is true, right? I mean, whatever those ij, k, or whatever rows are. So that's literally what is going on out here, right? I mean, if I were to write this guy, this part out here, if you kind of parse it in plain English, we are basically literally walking through the 1 rows. We are saying this row is 1, or this other row is true, or this other row is true, and so on and so forth. So we are basically saying f is equal to m8 is true, or m9 is true, or whatever minterm in this case, this is 6 1. Or I can even write them more compactly like this: summation of m, and then I just list the ones which are true. Okay, so this is just a convention. Okay. I could also write it in conjunctive normal form, and kind of the idea would be, in this case, I'm going to focus on the places where the function is not true. So what we will say is the which are the places when the function is false. So it's basically all the max terms. In this case, I don't know how many there are, 1, 2, 8, and 10 of those, right? So each one of these max terms, right, here, and so on, there are 10 of them. We are basically saying output is going to be 0 if any one of these max terms is 0, right? Because we are ending the max term. So if any one of those max term is 0, output is 0, right? So this is another way of saying, right, that we are just selecting those rows. Remember, max term takes the value 0 in its corresponding row. So if the inputs are such that, let's say they correspond to row number 1 here, right? Then the corresponding max term would be 0, and it will take the whole function down. So that's what's kind of happening out here. And this is the other way. Now here, obviously, there are more max terms. So the number of entries in the CNF, number of max terms in the CNF, plus number of min terms in the DNF will always add up to 2 to the power n, right? So that's what we're going on. So I'm going to stop out here. I think we can pick up here on Tuesday. So again, we covered a lot of territory today, but important concepts: min term, max term, DNF, CNF, and we saw some sort of properties of the Boolean functions kind of along the way. So before I hang up, any questions?
If so, you did the conjunctive normal form there. If you were going to set that equal to the function, would you have to take the negation of that?
No, right? Because what we are saying is function is 0 if any one of them is 0, right? I mean, so remember, because the max terms are being ANDed together. So if any of the max term is 0, the function is 0, which is exactly what we want. So we are focusing on the rows where the function is 0, and then the way, and max terms takes the value 0 in the corresponding row. So if I am, let's say, in this row, then max term number 2, right? This guy will have the value 0, and all the other will have 1. But since one of the max term is 0, so the function is 0, which is what we want, because we are looking at max terms for the 0 rows.
Okay, that makes sense.
So no dual needed.
Thanks.
Sure.